Hello everyone. So today's topic is sets and representation. So we start with sets. So set serves as a fundamental part of mathematics today. Set serves as a fundamental part. Set fundamental part of mathematics today. Mathematics today. Second, sets are used to define concept of relations and functions. Uh, sets are sets are used to define the concept of relations and functions. Relations and functions. And it is developed by German mathematician George Cantor. It is developed by German mathematician George Cantor. So this was about sets. Next we have sets and representation. Sets and representation. Sets and representation. Sets and representation. So what is set? Set is a well-defined collection of objects. Set is a well-defined collection of objects. For example, a crowd of people, and a set of natural numbers. So there is a distinction between these two. Crowd of people is a collection of objects, whereas set of natural number is a set. This is a collection because it is not well defined. Not well defined. As per definition of set, we can only call a collection as a set if it is well defined. So set of natural number is well defined, hence we call it a set. Next we have how to write a set. So how to write a set. uh, so first, objects. When we write a set, we have elements. So we have objects, elements, and members. uh, all are synonymous terms. That means if a set A is contains 1, 2, and 3, then 1, 2, 3 can be called as objects or elements or members. All three means the same. Second, the sets are usually denoted by capital letters. Sets are usually denoted by capital letters, such as A, B, C, X, Y, Z, etc. We never denote the set by numeral, such as if we say set 1 is equal to A, comma B, comma C. So this is the wrong way of representing a set. Set never comes with a numeral. designation. Third, the elements are represented by small letters. The elements are represented by small letters. Such as A, B, C, X, Y, Z, 1, 2. So elements can contain numerals, but that when we write a set name, then it is only designated by alphabet of English alphabet, letter of English alphabet. So set A, let's suppose set A contains 1, A, B, C. So this is a set name, and these are elements of set. Next, how to write whether an element belong to a set. How to write whether an element belong to set. So let's suppose let's say A is a set which contains 1, 2 and 3 as elements. Then we can say 1 belongs to A, 1 belongs to A, and 2 belongs to A, and 3 belongs to A. So symbolically we can write symbolically 1 is belongs to A, where E is epsilon, which means belongs to. Similarly, we have 2 belongs to A and 3 belongs to A. So if we have an element, if we have an element which is not which is outside the set A, which is outside set A, let's say element 4, 4 which is outside A, so we can say 4 does not belong to A. So this symbol means does not belong to. So this was about representation of a set. Next we will discuss two types of there are two types of set representation. So what are the types? What are the types of set representation? Set representation. So there are two types. First is rooster form, rooster, or we can call it tabular form. Second is set builder form. So first we will look at rooster form. What is rooster form? And all the examples we discussed above are form of tabular form or rooster form. So in rooster form, all the elements are separated by commas. All the elements are separated by commas. commas such as 1 comma 2 comma 3, and elements are enclosed within braces. Elements are enclosed within braces. Such as 1 2 3, and the braces is used are curly braces. Curly braces. We never use square brackets or round brackets. This is the wrong way. So only curly brackets are used. So this was about rooster type of set. Second we have set builder notation, set builder form. Set builder form. So what is set builder form? In this, all the elements of a set possess a single common property. All the elements of a set possess a single common property. A single common property which is not possessed by any element outside the set. Which is not possessed by any element outside the set. Second, we describe the element of a set by using a symbol X or any other symbol. We describe the element of the set by using a symbol X or any other symbol. So third and last point, after the semicolon, we write so after describing a symbol X, this symbol is followed by a semicolon. This symbol is followed by a semicolon. Then we write after semicolon we write the characteristic property of a symbol. Characteristic property of a symbol. So for example, we have a set V. This is in closed braces. Then we write a symbol X, which is followed by a semicolon. Then we write the property of X, which is X is a vowel in English alphabet. So this is a symbol, and this is a semicolon, and this whole description is a characteristic property of X. Characteristic property of X. So how do we read the set builder notation? So how to read set builder notation? Set builder notation. How to read set builder notation? So in the above example we have braces, colon and a symbol X. So braces means set of all, colon semicolon means such that. So we interpret the above example as follows: set of all X such that X is a vowel in English alphabet. Where set of all is braces and such that is semicolon. So this was about set builder form. Next we have two conditions when we write a set. Two conditions before finalizing a set. Before finalizing a set notation. First, order is not important. Order is not important. That is, if A is 1 comma 2 and A dash is 2 comma 1, then A is equal to A dash. So here order is not important. Second, repetition is not allowed. Let's say A is a set which contains 1 comma 2 and A dash is 1 comma 1 comma 1 comma 2 comma 2 comma 2 comma 2 comma 2. So in the set A we have two elements, and in set A dash we have 5 3 8 elements. So since repetition is not allowed, so A dash is reduced to 1 comma 2. Therefore A dash is equal to A. So repetition is not allowed and order is not important when writing a set. Next we have empty set. Empty set is a set which contains no element. Empty set contains no element. Example: A this. So there is no element in A and it is denoted by a curly braces blank or phi. So we can call A, write as A like this, or A is equal to phi. Example: A is a set for which X then followed by a semicolon, then we have range of X and 2, and X belongs to natural number. So this there is no natural number between 1 and 2, so A is a empty set, or A is equal to phi. finite and infinite set. Finite and infinite set. A set which is empty, which is non-empty and consists of definite number of elements is called a finite set. A set which is non-empty and its elements are countable. Then the set is finite. So if a set is finite, then the number of element is denoted by ns. Number of element is denoted by ns, where s is a set name and n is a designation number of sets, number of elements in set s. For example, A is a set which contains 5 elements 1, 2, 3, 4 and 5. So we write NA is equal to 5. So set A has 5 elements. Similarly, if A is 1, 1, 2, 2, 3, 3, 4, 5. So NA has 5 elements, because repetition is not allowed. It's not allowed. So 1 is repeated, 2 is repeated 2 times, 3 is repeated 2 times. We take only once these elements. Next, infinite set. Infinite set. If a set contains many elements such that ns is not defined. If a set contains for example, let G be the set of points on a line. G be the set of points on a line then n G is not defined, or Ng contains infinite elements. So how to write an infinite set? How to write an infinite set? So whenever we have an infinite set which is well defined, suppose we have a set of natural numbers, set of a natural number. So we write a few numbers first, 1, 2, 3, which is followed by 3 dots. So these 3 dots represent that the series continue indefinitely. This means series continue indefinitely. Also we have for example, let's take the above example. G be the points on the be the points on line, then n of g is infinite, so we can denote g as p1, p2 and p3, then three dots, where p is a denote the point on a line, where p means point on a line, point on a line. Also, infinite sets cannot be written in set builder form because elements of this set do not follow any pattern. Infinite set cannot be written in set builder form because elements of this set do not follow any pattern. Elements of this set do not follow any particular pattern. Next we have equal sets. So what is equal sets? If every element of A is also an element of B, and if every element of B is also an element of A, then A is equal to B. Or if two sets A and B are said to be equal, if they have exactly the same elements, then we write A is equal to B. For example, let's suppose A is a set which contains 1, 2, 3 and 4 elements, and B is a set 3, 4, 1, 2, 3, 4, 1, 2. So from the property of because we know order is not important, so we can say A is equal to B since every element of A is in B and every element of B is in A, so it implies that A is equal to B. Next we have topic subsets. So set A is said to be a subset of B if every element of A is also an element of B. A set A is said to be a subset if every element of A is also an element of B, so it is denoted by a symbol. It is denoted by a symbol, this elongated C, that is A is a subset of B, or or A is a subset of B if element A belongs to A, then A belongs to B. So mathematically we can write mathematically A is a subset of B if A belongs to B, implies A A belongs to A implies A belongs to B. So that is A is a subset of B if an element A belongs to A implies that A also belongs to B. So this symbol means implies. So we interpret this as follows: A is a subset of B if element A belongs to A, which implies element A belongs to B. So what if set is not a subset of any other set? Then we write A is not a subset of B, where the symbol with a cross sign means does not is not a subset, is not a subset. So note, for any set A to be a subset of B, then every element of A should be in B. For A to be a subset of B, then every element of A should be in B. Should be in B. So it is possible that every element of B may or may not be in A. So if B is a subset of A and A is a subset of B, then A is equal to B. Or mathematically we write, if B is a subset of A and A is a subset of B, which implies A equal to B. So this symbol means if and only if So we have some special note, that is, any set is a subset of itself. Any set is a subset of itself. An empty set is a subset of every set. So what does this mean? That if A is a set 1 2, then phi is a subset of A, and if we write A is equal to 1 2 and another set A 1 2, so every element of A is a subset of itself. So this is empty set which is a subset of A. So any set is a subset of itself, and empty set is a subset of every set. uh, so what is proper set and superset? What is proper set? What is a proper set and a superset? If A is a subset of B and A is not equal to B, if A is a subset of B and A is not equal to B, then A is called proper subset, called proper set of B, and B is called superset of A, and B is called so if we write A is a subset of B, uh, A is a subset of B and A is not equal to B, then we can say A is a proper set, A is a proper set and B is a superset. So what is a singleton set? What is a singleton set? Any element, any set which contains only one element. Any set so for example, A equal to A, so it is a singleton set because it contains only one element A. It is a singleton set. Also, empty set is not a singleton set. Empty set is not a singleton set. So again, we have a note. It is very important. So element of a set can never be a subset of itself. Element of a set can never be a subset of itself. For example, we have a set which contains one element, and set B contains three elements, 2 3, and B contains only two elements, C contains three elements. So here 1 is an element, and here 1 is not an element, 1 is not an element, but this 1 within braces is an element. Similarly for C we have 1 is not an element and other 2 and 3 are elements. So we can say A belongs to B because A is a whole set which is an element in set B, which is an element in set B. And we can say B, every element of B is in set C, so B is a subset of C. So from this we can say A is not a subset of C. So the conclusion is element of a set can never be a subset of itself. So element of set A can never be a subset of itself. So there are some standard subsets as a set of real numbers. Standard subsets, subset of a set of real numbers. There are many subsets of real numbers such as n, natural numbers, z, integers, and q, rational numbers, and t, irrational numbers. So mathematically n is a subset of z, is a subset of q, is a subset of r, and t is a subset of r. So n is the smallest set and r is the largest set. And natural numbers is not a subset of irrational number. So this was about subset uh, of natural numbers, integers, rational numbers, and irrational numbers, which are a subset of real numbers R. So we can call R as a universal set. Universal set. So what are intervals of subset? So what are intervals? So when we have a large finite set, then we represent the set in interval form. When we have a large finite set, then we represent the set in interval form. So there are two types of intervals. There are two types of intervals. Closed interval, which is represented by square brackets, and open interval, which is represented by round brackets. So closed interval, let A and B belongs to R. Let A is an element and B is an element which belongs to R, and A is less than B. Then the set is set of real numbers, set of all real numbers between A and B. y, and is a this is called a closed interval. It is denoted by square brackets. For example, 2 comma 5, which is equal to 2 3 4 5. So if we represent this on number line, so this is 2, this is 5, and this is a solid this is a solid circle, which means that the endpoints, the 5 is included in the set. Similarly for 2, and we also include the midpoints between 2 and 5, 3 and 4. Next we have open interval. Open interval, same as the a and b belongs to R, where a is less than b, then set of all real numbers, then set of all real numbers y, where a and b and a comma b belongs to R. Then we have it is denoted by round brackets a comma b. For example, 2 comma 5 is equal to 3 comma 4. So on number line it will look like this: 2 and 5, 2 and 5. So this is a whole, because 2 and 5 are not included in the set. Only 3 and 4 are included in the set. So this represent open interval. There are two special type of intervals. Special special type of intervals. First is interval including a but not b. Interval including a but not b. Second, it is denoted by close bracket a and open bracket b. For example, 2 comma 5 is equal to 2, 3 and 4. So if we represent this on number line, we have closed side on b and open side on 5. So we have solid on 2 side, solid, and a circle on 5 side, and a hole on 5 side, hole. So we do not include 5 in the set, we only include 2, 3 and 4, 3 and 4. Second interval is when including b but not a, and it is denoted by a comma b. For example, 2 comma 5 is written as 3, 4 and 5. So on number line, 2 represent a whole and 5 represent a solid. 2 represent a whole and 5 represent a solid. Again, 2 is excluded from the set because it is a whole, and we include 3, 4 and 5. So next we have what is the length of the interval. What is the length of any interval, length of any interval. So length is given by b minus a, because b is always greater than a, so length is always greater than 0. For example, we have a set 2 comma 5, so its length is 5 minus 2 equal to 3, so it's greater than 0. Power set. What is power set? The collection of all subsets of a set A is called a power set of A. The collection of all subsets of set A is called the power set of A. Is called the power set of A. It is denoted by PA. It is denoted by PA. For example, if we have A is a set 1 comma 2, so PA will be include 5 1 2 1 comma 2. So in general, if A is a set, with NA equal to M elements, then number of elements in power set will be 2 to power m, 2 raised to power m. Example, if set A contains 1 comma A comma B comma C D comma 3, so we have NA equal to 7 elements. So if we take a power set of A, then power set of A should have 2 raised 7 elements, that is 128 elements. So this was about power set. Next we have universal set. So universal set is a basis set. It is a basis set, and it is denoted by U. For example, we have a set of prime numbers, set of all prime numbers, which is a subset of set of all numbers, which is a subset of set of all natural numbers. Then we can say N is a universal set. N is a universal set, and P is a subset of N. So P is a subset of N, so where N is a universal set. Next we have a Venn diagram. So they are used to show relationship by means of a diagram. They are used to show relation by means of diagram. Second, the diagram are generally rectangle and closed curves. So diagrams are generally rectangles and closed curves and closed curves. Third, where rectangle is a universal set and a closed curve such as circle is a subset. Where rectangular, generally closed curves are circle. So rectangle is a universal set and circle is a subset. For example, we have example u equal to 1 comma 5 6 7 8 9 10. So universal set contains 10 natural numbers, and we have a set A which contains even natural numbers up to 10, 2 4 6 8 and 10. So if we write a diagram, then we have this. So this is a rectangle where A is a subset, and U is a universal set. So we have elements 1, 5, 9, 3 and 7, and we have 2, 4, 6, 8 and 10. So this is a representation of a set via Venn diagram. Next, we have another example. If U is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and A is equal to 2, 4, 6, 8 and 10, and we have another set B which is equal to 4 and 6. So how do we represent it in Venn diagram? So first we construct a rectangle. Rectangle. This is a rectangle, and we have set A which is A, and B will be inside A because B is a subset of A. So this is a set B which contains 4 and 6, and A contains 2, 4, 6, 8, 10, and 1, 3, 5, 7, 9. So this is how it will look like. So next we have operations on sets. Operations on sets. Like in algebra, we do addition and subtraction. There are operations involved in the set such as union operation, and intersection, and difference of set. So first we'll look at a union of a set. A union of a set. What is a union? So union of two sets is the set C. Union of two sets A and B is the set C, which consists of all those elements, which consist of all those elements which are either in A or in B, which are either in A or in B. So symbolically we write A union B. So this symbol means union, or so in set builder form x belongs to A, or x belongs to, so or also represent a union operation, So in Venn diagram, uh, how do we represent a union? So if we have set A and set B, so union will be all the elements belonging to A and B, where common element, common region is taken only once, is taken only once. For example, A is equal to and B is equal to A, I and U. So in Venn diagram, so in Venn diagram we have so in Venn diagram we have this where A is a set and B is another set. Uh, so we have this A is a set and B is a set, A and B. So A contains A, E, I, O, U. So A, O. We write common elements in between in center region, A, E, O, and this. So this is 0. There are no elements in B which are not common with A. So this is 0 and this is letter O. So when we write A union B, we have A, E, I, O, U, where common region A, I, U is taken only once. So there are some properties of union set which will be helpful in solving examples problems. Uh, so first is A union B is equal to B union A, commutative law. Second is A union B and union C is A union B union C, so associative law. Third, A union phi equal to A, and it is known as law of identity element. Law of identity element. Fourth, A union A is equal to A, so it is idempotent law. Five. So U union A is a universal set, so this is a law of U. Law of U. And next we have intersection of a set. Intersection of a set. Intersection. So what is intersection? So intersection of two sets A and B is the set of all those elements which belongs to both A and B. All those elements which belongs to both A and B. So mathematically we have A intersection B. This is a symbol of intersection. So X, where X belongs to A and X belongs to B. So and is a symbol of intersection, and means intersection. For example, A is a set which contains 10 natural numbers 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10, and B is a set which contains 2, 3, 5 and 7. So we have a common elements as common set will be 2, 3, 5 and 7. So if we draw a Venn diagram, it will look like this. We have a rectangle and this is set A and this is set B. A and B. So 2, 3, 5, 7. So this is the intersection part. This is intersection. So we have a note here. If A and B are two sets, if A and B are two sets, then A intersection B is phi. Then A and B are called disjoint set. Then A and B are called disjoint set. Since there are no common elements, hence since there are no common elements, then A intersection B is of null set is equal to phi null set. So in Venn diagram it will look like this. We have two sets A and B. So there is no intersection between two sets. There is no common elements between two sets. So no common region. No common area. Hence the sets are disjoint set. There are properties of intersection. There are properties of intersection. First, we have A intersection B is equal to B intersection A. So it is a commutative law. Second, we have A intersection B intersection C is equal to A intersection B intersection C, which is associative law. Third, we have phi intersection A is equal to phi and U intersection A is equal to A. So law of phi and this is the law of U. This is law of phi. Fourth, A intersection with itself is a A. This is idempotent law. Idempotent law. And last we have A intersection B union C. A intersection B and union A intersection C. So this is distributive law. So this was about intersection of sets. Next we have some operations which involve three sets. Operations involving three sets A, B and C. So first we have B union C. So if we draw a Venn diagram, then it will look like this: A, B. So B union C will be A, B, C. So all the elements including B and C, whether you have A common elements A or not, all the elements of B and C, including some part of A, second we have uh, A intersection B. So it will look like this. This is set A, this is set B, and this is set C. A and B and C. So A intersection B will contains all the common elements with the elements of those which are intersected by C. So we will not exclude the elements which are intersected by elements of C. So this is how it will look like A intersection B. Next we have uh, A intersection B union C. So in this first we will draw B union C, and then we superimpose with the set A. So this is A B. So what is B union C? So B union C will be all the elements of B and C. All the elements of B and C. Plus, next we will take A intersection of B union C. So we have this set A, this and this. So we have A intersection B intersection C. So it will look like this. So this is a final set. Next we have A intersection C. So we will draw A, B and C. So A, B and C. So A intersection C will be all the common elements between A and C, including those parts of B which are intersected by A and C. So this is a part which is intersected by B. So we take all the elements of A and C. Next we have A. Next we have A union B intersection A intersection C. So first we will draw A intersection B and A intersection C, and then we'll take a union of both the sets. So A intersection B, this is A, B, C. A intersection B is this, and A intersection C, A, B, C. So this is the A intersection. Then union will contain, so A intersection B union A intersection C will contain all the elements of A intersection B and A intersection C, A intersection B and A intersection C. So next we have a difference of sets. Difference of sets. So difference of set A and B in the order is a set of elements which belongs to A but not B. So the difference of the set A and B in the order is the set of elements which belong to which belongs to A but not B. So we write symbolically as A minus B. For example, A is a set which contains 1, 2, 3, 4, 5 and 6, and B is a set which contains 2, 4, 6, 8. So A minus B will be 1, 2, 3, 4, 5, 6 and 2, 4, 6, 8. This is minus sign, and this is 2 cancel out, 4 cancel out and 6 cancel out. So remaining in is 1, 3 and 5. So A minus 3, 1, 3 and 5. Note that A minus B is never equal to B minus A. So if in the above example, if we take B minus A, then we have 2, 4, 6, 8 and 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, and we take a minus sign, then we cancel out 4, so only 8 is left. So which implies B minus A is not equal to A minus B. So in Venn diagram we represents A minus B and B minus A as follows. So this is a Venn diagram. This is set A and this is set B. So this horizontal line, this is a region of A minus B, and this vertical line region, this is B minus A. So what are disjoint sets? What are disjoint sets? Disjoint sets. So set when there is no common region between sets. When there is no common elements, common region, then the sets are disjoint sets. For example, we have A minus B and A intersection B and b minus a, b minus a. So these all three sets are mutually disjoint sets. These are mutually disjoint sets. So if we draw a Venn diagram, this is a rectangle. This is a rectangle where this is a set A and this is a set B. So if we draw, so this yellow region is this yellow region is this is A minus B, and this green region is so this green region is A intersection B, and we have this blue region. This blue region is B minus A. So we see here that there is no common elements between A minus B and B minus A and A intersection B. So these three sets are disjoint sets. Next we have a complement of a set. Complement of a set. Complement of a set. Complement, or we can say negation of a set. So let let U be the universal set. U be the universal set, and A is a subset of U. A is a subset of U. Subset of U. Then complement of a set. Complement of A is the set of all elements of U which are not the elements of A. So this is denoted by A dash. This is denoted by A dash. So A dash is in set builder form. We can write it as follows: x belongs to U, universal set, and x does not belongs to A. So mathematically A dash is equal to U minus A. For example, we can take example. Example, U is equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. A is equal to 1, 3, 7, 9. So A dash is equal to U minus A. So we subtract like the previous we have done: 3, 4, 5, 6, 7, 8, 9, 10. So 1, 3, 7, 9. So 1, 3 and 9 and 7. So we are left with 2, 4, 5, 6, 8 and 10. So A dash is equal to 2, 4, 5, 6, 8 and 10. So this is A dash. So now there are properties of complement of a set. Properties. First is complement laws. Complement laws, where A union A dash is a universal set, and A intersection A dash is a disjoint set, so it is a null set. Second, we have De Morgan's law. De Morgan's law. So we have A union B complement is equal to A complement intersection B complement, and second we have intersection B complement is equal to A intersection U union B complement. Third, we have law of double complement. Law of double complement, which states that A complement of A is a set of A itself. So fourth, we have law of empty set. Law of empty set, which states that complement of null set is a universal set. And fifth is law of universal set. Law of universal set, which states that complement of a universal set is a null set. Next we have what is De Morgan's law. What is so De Morgan's law. The complement of the union of two sets is the intersection of their complement. The complement of the union of two sets is the intersection of their complement. And the complement of their intersection, complement of intersection of two sets is the union of their complements. So complement of intersection of sets is the union of union of their complement. So mathematically, A intersection B complement is equal to A intersection union B complement. So we take an example to illustrate the De Morgan's law. We take a universal set 1, 2, 3, 4, 5 and 6, and A is equal to 2 comma 3 and B is equal to 3 comma 4 comma 5. So we have to find A intersection B. A union B complement is equal to uh, A complement intersection B complement, which is De Morgan's law. So first we will find A dash, which is U minus A, which is given by 1, 4, 5 and 6. Then we find B dash, which is U minus B, is equal to 3, 4, 5, 1, 2 and 6. Next we will find A union B. A union B will contain all the elements of A and B, 2, 3, 4 and 5, while taking common elements only once. Now we will take A union B intersection complement, which is equal to U minus A union B, 2, 3, 4, 5, 1 and 6. So this is first equation. Next we have A uh, complement intersection B complement. So we have 1 and 6. So from here equation 1 is equal to equation 2. Therefore De Morgan's law is verified. A union B complement is equal to A complement intersection B complement. So there are some algebraic relation between operations. So this is the last topic of the chapter sets, which is algebraic relation between operation, which is algebraic relation between operations. So we have algebraic relation between operation. So first we have number of elements in A union B is equal to number of elements in A plus number of elements in B minus number of elements in A intersection B. So if we have a Venn diagram, this is A set and this is B set, then we have A, B, and so N A union B. So this is N A and this is N B, and this region is N A intersection B. Second we have if there are three sets A union B union C is equal to NA plus NB plus NC minus NA A intersection B minus NB intersection C minus N A intersection C plus N A intersection B intersection C. So in Venn diagram it will look like this. This is NA, this is NB, and this is NC, and this region is NA intersection B intersection C. So let's take an example. So we have x and y are two sets, x and y are two sets such that x union y has 50 elements, x and x union y has 50 elements, and x has 28 elements, and ny has 32 elements. So according to so we have to find an x intersection y. So we take n x union y, which is equal to nx plus ny minus n x intersection y. So this is 50, this is 28 and 32 minus n x intersection y. So n x intersection y is equal to 10. So this was about algebraic operations, and this is the end of our lecture. So thank you. I hope you like it.